Okay, let's go ahead and continue our discussion of the chain rule with some problems here. Okay, if you remember last time, if z is a function of x and y, x and y themselves are a function of some independent variable t, okay? And I'm assuming all these functions are differentiable. By the way, some people like to actually give a different name for this function here. Okay, so they might have g and h here instead of just x is x of t, y equals y of t. But I don't see any particular reason in the examples I'm taking to do that. Okay, but sometimes you will notice that. Okay, in some books and things. Okay, what would the chain rule say if all these functions are differentiable? Well, the derivative of z with respect to t, or f with respect to t, if you prefer to write it that way. Um, Really, I like it writing z because you think of it this way as a function of x and y, where x and y are functions of t. But anyway, this is going to be the partial derivative of f with respect to x times dx over dt plus the partial derivative of f with respect to y times dy over dt. This is simply what? You guys see this as an example of the chain rule. Okay? Here's sort of a visual way sometimes people like to write this. I've got my original independent variable here. X and y are functions of that independent variable. So I've got a line going from t to x, okay, indicating that x is dependent upon t. And the same thing here with the y. On the other hand, z is dependent upon both x and y, so I've got x and y together coming into z, so they're both pointing at z. Okay? Now, I think of these as, if I think of x as a function of t here, I can talk about the derivative of x with respect to t in the case that it actually is differentiable, as I've mentioned. And the same thing over here, dy over dt. So I'm going to label these particular directed line segments with dx over dt, dy over dt, and likewise these directed line segments entering z with partial derivatives here only, though, right? So I'm going the partial derivative of f with respect to x and y because df over dx itself, if those were d's instead of del's, that would make no sense, right? Because z is dependent upon both x and y. Well, at least it would make no sense unless y was dependent upon x also. Okay, that would be an exceptional case. All right, but in general, no. Okay, now, how do you get the chain rule? What you do is start from the ultimate independent variable and end at the dependent variable. And what you do is, as you follow the directed arrows to get from t to z, multiply by all the values along those directed arrows and add them up. Okay, so we could get from t to z by following these upper directed arrows. Those labels on those arrows are dx over dt and partial derivative of f with respect to x. Multiply those together, okay, and then add what? The same thing, only following the bottom arrows. Okay, so I've got the partial derivative of y with respect to t times the partial derivative of f with respect to y. Now, this idea could be extended. You know, we might have another variable, w. Okay, maybe z depends upon x, y, and w, in which case I would have what? A third arrow. Okay, and some partial derivatives and some whole derivatives involved. Okay? Alrighty? I'm not sure if that helps or not, but some people like to think about writing it that way. Okay? All right. I've starred this particular example because I always like to give one like this on the exam, so be looking for a question of this kind. I'm not sure if the book has questions of this kind, so you do need to pay attention to a question like this. Okay, z is a function of x and y. X and y are both functions of t. All these are differentiable functions. Okay, some parameters involved. X is equal to 3 when y is equal to, or when t is equal to 2. So we could say x of 2 is equal to 3. Likewise, y of 2 is equal to negative 1. X prime at 2 is a half. Y prime at 2 is negative 2. So these are just parameters I've given you. This is part of the given. Okay. F sub x, okay, so that's the partial derivative of the function x with respect to x, right? When x is equal to 2 and y is equal to negative 1 is 4. And likewise, f sub y at 3, negative 1 is 5. Okay, so these are just parameters given to you. And what is the question here? The question is to find dz over dt at t equals 2. Okay? Alrighty? Well, I've actually noticed that I haven't given you any formulas for f of xy, right? Okay? It's just all numbers. Okay? But I've given you enough information that if you know the chain rule, you should be able to actually compute its value. Well, let's come back here. Let's look at the chain rule. What would the chain rule say if all these functions are differentiable? It would say dz over dt is f sub x times dx over dt plus f sub y dy over dt. Okay? I've actually written dx over dt and dy over dt as x prime and y prime of t, respectively. Okay? And then I've also included, for emphasis here, remember x and y are functions of t, so I put in x of t, y of t in both cases here. Okay? Now you're evaluating up here, I've circled here, x equals 2. So dz over dt at t equals 2 is f sub x at what? X of 2, y of 2, x prime of 2, f sub y at x of 2, y of 2, y prime of 2. So I've just put in place of t everywhere, the value 2, right? Okay? So I've used slightly different notation. Instead of Leibniz, I've used the prime notation, but this is it. Okay? Does that make sense to you? Okay. All right. This notation, by the way, if you remember, this just means you're evaluating what comes before it at t equals 2. Okay? Now, what is x of 2? What is y of 2? Well, if you look above, they were actually, what, 3 and negative 1, respectively. So I can fill in those values right there and there. Okay? The rest of these get carried through, x prime of 2, y prime of 2. Okay? So just saying literally what these values are. But wait, remember above I gave you those values. I said what? F sub x at 3, negative 1 is 4. F prime at 2 is a half. F sub y at 3, negative 1 is 5. And y prime at 2 is negative 2. So I just put in those numbers and add them all together, and I ended up getting negative 8 for my final answer. Okay? Alrighty? So you want to go ahead and review this question, okay, because you'll see one like this on the exam. Okay? It should be a piece of cake, actually, if you know the chain rule. Notice no formulas given. That was what was interesting about it. Okay? I mention a question like this because in many cases you can get away with not actually using the chain rule. You can just use Calc 1 in the case of a single ultimate independent variable here. So for example, suppose that z is f of xy is 3x squared plus 4y squared. X of t is e to the t, y sub t, or y of t is the natural logarithm of t. I'm having t be greater than 0 here, so this function, natural logarithm, exists, okay, and is differentiable for t greater than 0. Okay, you can see all these functions are then differentiable, right? Okay, find the partial derivative of z with respect to t. Okay, let's go ahead and just use the chain rule. You're going to differentiate this whole thing, z, or f if you wish, with respect to x, and you would get what, 6x? Okay, so that goes in there. The whole derivative, of x with respect to t is e to the t. The partial derivative of z with respect to y, okay, would be what? 8y, so that goes in there. And the derivative of y with respect to t is 1 over t. and you could put those all together like that. And notice in the end what I've done here. I've replaced x by e to the t and y by the natural logarithm. So I wrote my final answer entirely in terms of t. You didn't necessarily have to do that. You could have stopped up here. Okay? All right, for many questions that you will see in the homework for the book, they will stop up here. Okay? Let's come back here. Let's just double check by substitution. Okay, so this is a Calc 1 way of working this problem. Well, I'm sure you could see it here. Remember, z is 3x squared plus 4y squared. I could just substitute for x, e to the t, and for y, the natural logarithm of t, stick them in there, and this is my function in terms of what? In terms of t, and then what? Directly differentiate with respect to t, okay? And if I do that, don't forget the chain rule, the simple Calc 1 chain rule here. That's a composition, right? Natural logarithm of t squared. But I get exactly the same answer in either case. Okay? All right. See how I got around using the chain rule by just using substitution? I could, like I said, I could do that in the case of a single independent variable. Okay, that does not abrogate your need to learn the chain rule, however. Notice that you could not use that trick on question here that I asked. Okay, this one. Nope, you couldn't use that trick. There's no substitution that you could make or anything. That's why I like questions of this type. There's no getting around knowing the chain rule to answer this question here that I've starred. Okay? All right. Now, here's another thing you need to know, the chain rule with multiple independent variables. Okay? Now, I'm not going to show you the entire proof of this thing, but it works. I think your book writes this out. But it works in a similar fashion to the regular chain rule that we mentioned previously, okay, in the case of a single independent variable. But let's give you an example here. Suppose z is a function of x and y, but x and y are functions of two independent variables, u and v. So you can see with substitution that z is ultimately depending on what? U and v. Now I'm going to assume all these functions are differentiable. Okay? You could talk about what? The partial derivative of z with respect to u. Okay, you see how we need the del's here? Because what? Z would ultimately depend upon what? Both u and v being independent variables. So I'm going to need a partial derivative here, right? So I've got those del's in here. Okay? Now, what's the rule? What's the chain rule in a case like this? Well, it's very similar to the previous chain rule, only you have to remember, see, if I'm going to do this, the partial derivative of z with respect to u, okay, first z depends upon x, but since it depends upon both x and y, I'm going to have instead of, I'm going to have dz over dx, and here the difference is I'm going to have what? Partial derivative of x with respect to u instead of dx over du, because what? X depends upon two independent variables, both u and v. Okay? And then what? Keep going. Wait. Z also depends upon what? Y. So I need to take into account changes in y also when I'm talking about changes in x. But remember, y also depends upon u and v. So I've got my chain rule looking like this. Okay? And something very similar here. Only when I'm taking partial derivatives of z with respect to v, just everywhere it looks the same except for I've done what? I've replaced u by the independent variable v. Okay? I guess in accordance with my previous way of writing it, I really should have written these products in the opposite order. Multiplication being commutative, it's not going to matter in the end, but maybe I should have done that. Okay? And the same thing here. But okay, this is the idea for the what? The chain rule in the case of multiple ultimate independent variables. Okay? Let's go ahead and take an example. Suppose z is the natural logarithm of x squared plus y. Okay? And let's suppose that x equals u plus v and y is u squared minus v squared. I want to know the partial derivative of z with respect to u and v. Okay? Alrighty, so what are we going to do? We're going to go like this. We're going to take the partial derivative of z with respect to u. The first thing, we're going to take what? The partial derivative of z with respect to x, right? So that would be the reciprocal. Okay? 1 over x squared plus y. Don't forget to multiply by the partial derivative with respect to x, which gives us the 2x, right? So it's 2x over x squared plus y. And then what? Multiply by what? The partial derivative of x with respect to u. You can see that's really easy. U and v are independent variables, so you're holding v constant. So the derivative would be what? 1. There we go. And the same thing here. 1 over x squared plus y. Okay. Very similar when I differentiate with respect to y, only a little easier. Okay, so 1 over x squared plus y. And then multiply by what? The derivative of y with respect to u. So that would be 2u. And then I'm going to do the same thing with the v's. Okay, notice these get carried right down, so I don't have to perform new calculations here. Those get carried right down here. These do not. Okay, I've got to take the partial derivative this time with respect to what? V. That happens to be 1 also. Okay, and then I have to multiply by the partial derivative with respect to v here, and it's going to be what? Minus 2v. And there, you know, I could rewrite these if you like it in a little more succinct fashion here, but these are ultimately the partial derivatives. Okay, next time we're going to talk about implicit differentiation. I hope you understood that. That'll be good for now.